sea by the dawn. Words have lost their meaning, but we're carrying on, and I believe.
Hi, I'm Juha and I'm a hockey player here at USC. I will be going through some physics concepts and examples with you this semester. And remember, just like on the ice, there's no such thing as luck in physics. Just keep your head up and work hard. Here we have a system of a mass, and that's been wound by a rope around a pulley or a wheel, to be more exact. And when this mass is released, it falls 3 meters in 2 seconds with constant acceleration. And we would like to know, what is the mass of the wheel, the capital M? First of all, we are going to need the final velocity of this mass. So let's find out that one first. And let's say that this object falls, that's the delta H. It falls in 2 seconds, about 3 or exactly 3 meters, like this. So how do we find the final velocity? So from our cheat sheet for motion with constant linear acceleration, we have to look the one that involves final velocity and distance, or final velocity, distance and time, and that is the last one here. So we'll use this one, because from here we can solve for Vx, because when we know the V initial, which is, by the way, 0, and then we know the change in displacement, which is delta H. So going from there, we get 2 times delta H divided by T equals V0. So that's just 0 plus V. That's the V final. We just call it V. So V is 2 times the delta H, 3 meters, divided by 2 seconds. So the final velocity is 3 meters per second. And what can we do with that? We are trying to get our hands to the moment of inertia, because that's where the capital M, the mass of the wheel, resides. And that leads us to, of course, the conservation of energy. And part of it is the rotational kinetic energy of the wheel. So if this is our 0 level for the height, then in the beginning we only have the gravitational potential energy of the falling mass, and we have mg times delta H. And in the end, that is converted into the kinetic energy of the falling mass with velocity v that we just calculated, and the rotational kinetic energy of the wheel, which is half times I omega squared. And omega is the linear velocity, let's say for like one of the points on the wheel, divided by the radius. And this linear velocity of this point is of course the same as that of the mass, because they're connected by a tight rope. So what we can do here is to write the omega as v squared over r, and here we still have mg times delta H. Now let's multiply by 2, so both sides, so we have 2mg here, and we try to isolate the I, so bring that one over there. So in that case we get m times 2g delta H minus v squared equals I times v squared over r. Well, that's going to be r squared, of course, like this. And from here we can solve for the moment of inertia to be m times r squared 2g delta h minus v squared divided by v squared. So the mass of the falling object, that's 4.2 kg. And then we have the radius of the wheel squared, 0.28 meters squared, times 2 times 9.81 meters per second squared, times the delta h, which was 3 meters, and then we have the velocity squared. It's going to be tight, so that's going to be 3 meters squared, 3 meters per second squared, so minus 9 meters per second, both squared. And whole thing divided by v squared. And we get 1.82 kilograms meter squared for the moment of inertia. And how do we find the mass from there? So we know that for a uniform cylinder, which this essentially is, we only see it in 2 dimensions though, but it is a cylinder like this, although a thin one. Nevertheless, the moment of inertia of the wheel is, we can look it up from the table, half times the whole total mass radius squared. And we solve for the mass, so we get 2 times I of the wheel and divided by r squared, and that's m. So 2 times 1.82 kg m squared divided by the radius squared, 0.28 meters squared. So we get units of kilograms, and that gives us 46.4 kg. So roughly 46 kilograms is the mass of the wheel.